Well, welcome back to the Cave of Science, and we're looking at the review for the cosmology assessment we took, and so we'll get on with it. One thing many of us are forgetting on the first sheet of all these assessments is explain and complete sentences. So don't be surprised on the next assessment. This will start to factor into your grade here. We've been doing it all year, and for whatever reason on this last one, the complete sentences really took a back seat here. All right, so let's look at the first question. If the sun's mass was 3 times larger, well, we know if it's gets much bigger than the mass of a star gets much bigger than the sun, it's going to form a black hole. And we also know black holes are at the center of different galaxies, of which our Milky Way is one. And we want to also describe its gravitational field. The gravitational field is so strong that light cannot escape from a black hole, hence the term black hole. And we discuss these in class and also on the lecture, so nothing too surprising on this one. Elements lighter than iron, other than hydrogen and helium, and hydrogen, was really at the Big Bang, and helium, quite a bit of that was there also, are formed during what process in the star's interior? Well, the light elements are formed from fusion. And fusion is taking two hydrogens and making helium and having some energy left over. And as a star goes through its main sequence lifetime, many of these lighter elements, such as helium, are fused into other elements. The heavier elements, other than iron, are formed during planetary nebulas. And this was off a lecture we talked about in class, and it was also on some of the couple of the sites I told you to use for some background information. So that was the first one, pretty short unto itself. So we'll look at the next one now. The next one is the Big Bang Theory, and again, make sure you start writing in complete sentences. So the first question here, explain the two pieces of evidence that support the Big Bang Theory. One is the redshift, which was near the end of the lectures and that we looked about. As everything's expanding, with the whole idea of the Big Bang Theory, the expanding universe, everything in the universe is moving away from each other. And it's really the Doppler effect. And we discussed that at some length when we talked about waves earlier this year. And so one piece of evidence is the redshift. The other one is that leftover radiation from the Big Bang, or cosmic microwave background radiation. And I believe that was right off the first lecture. And these are the two really big pieces of evidence that support the expansion of the universe, or the Big Bang Theory. This element was produced by the Big Bang. And why is it important to formation of stars? This answer, I guess I forgot to put in, but this is going to be hydrogen, and hydrogen is the fuel for the whole process of fusion. Two hydrogen atoms fuse together to form helium, and hydrogen's the lightest element, and this is the element that is by far in the greatest abundance in the universe. The next one, explain two forces that contribute to the formation of stars and planets. Well, stars and planets are formed in these nebulas, and what starts pulling things together is gravity. If it has mass, there's a gravitational pull between different masses, and as gravity starts pulling all this gas and dust together, as it starts pulling more and more together, you start getting that pressure. And once that pressure gets great enough to fuse hydrogen, that ignites the star. And so the two forces are gravity and pressure. This next one here, we got a standard spectrum and visible light. And we can see from here, here's the standard one, we can see everything was shifted to the infrared side, or the red side. Well, what conclusion can be made? Well, we know it's shifted to the infrared/red side, and that is one of the whole ideas of evidence for the Big Bang Theory. So the spectral lines have been shifted towards the infrared, and the star is moving away from Earth. If the stars were moving towards the Earth, or if it was a contracting universe, they'd been shifted towards the blue or the ultraviolet. And that would be a whole idea for attraction, or A. But in this particular case, we looked at the expansion of the universe. It's again, use the test as a source of information. And this question was already really kind of asked in a previous question, and it's the whole idea of the redshift. The spectrum is shifted to the red. This goes back to the star composition activity that we did in class. All right, I think that's the last one there. So let me pull up the next one, sun infusion, and we'll pull this over. And let's go down here, get through it. The above process provides energy for the sun. Answer the following questions. What's the name of this process? Well, two hydrogens form helium, and that's the whole idea of nuclear fusion. What does this process produce? Well, we know energy's got to be one. That's right up here in the equation, and the other one is helium. And we talked about this, and is also off your lectures in class there. For how many more years will this process continue? Approximately 5 billion years. The sun is a main sequence star about halfway through its lifetime. And if you remember, once the star gets through its lifetime, it'll jump off the main sequence to become a red giant, and it'll go through a planetary nebula, white dwarf, and then it'll slide over to the brown dwarf. Energy is transferred in three ways. The big one here is really you have radiation and convection. And again, I pretty much let either one go here. Again, complete sentences. Many of you did not write your answer in complete sentences. Here we had to put the whole idea of the stages in the correct order. And so the first one was A. Stars start out as clouds of gas and dust drifting through space. The next one is F. Gravity starts pulling these things together, forming clumps called protostars. And then once you get enough heat and pressure in the core of the protostar, nuclear fusion will take place. And if nuclear fusion takes place, you're going to get the igniting of a star, causing it to shine. After the star goes through its lifetime, most of them on the main sequence, it begins to run out of fuel, excuse me, and expands into a red giant or a red supergiant. From there, it'll go to a planetary nebula, and then, in the case of our star, it'll go to a white dwarf. Now, if the star is a whole lot bigger, or 3 times the sun's mass, it can go to a black hole. So it really depends on the mass of the star. The next question dealt with a Hertzsprung-Russell diagram. We can see we have the main sequence right in here. We have the red supergiants in the upper right hand corner, blue supergiants in the upper left hand corner, white dwarfs in the lower left hand corner. And this is pretty much the same 2 activities you did in class, and also the lecture where I pretty much split the Hertzsprung-Russell diagram into quadrants. So state the relationship between X and Y. Well, as we can see, as temperature increases, we know magnitude will increase, but it's also dependent upon the mass of the star. We've got white dwarfs here, have very high surface temperature, but they're not very bright because they are not very massive. So again, you got to throw that whole idea of mass in there also. Number 2, most stars belong to this category, right here on the graph, of which our sun is a member of the main sequence. Talked about numerous times in class, most stars belong to the main sequence. Which categories of stars are most likely to form black holes? Well, those are the blue-white giants. Remember, we talked about the red giants were at one time main sequence stars, and if they're main sequence stars, they're not going to be large enough to form black holes. So we're really looking at those blue giants or the blue supergiants, very, very massive stars. The Sunspot Cycle, this is the exact same thing you did for the activity in class. There's about a 10 to 11 year interval between sunspot maximums, and sunspot maximums correlate very nicely to the number of magnetic storm days. and it's exactly really it's the same question that you answered on the activity and that we also talked about in class. And I think that's it for that one. So let me pull up the very last one, which is going to be Kepler's laws. Bring this over. All right, let's look at Kepler's laws, of which we did a lot of work on. And I gave you the formula here. The first formula, the period or the time it takes for a planet to orbit a sun, the square of that, or that squared, equals the distance in AUs cubed. And then eccentricity equals the distance between the foci divided by the major axis. So both those are there for you. Okay, the first one, we got to theoretically decrease the gravitational force in two ways to theoretically increase. Well, if we want to decrease the gravitational force, there's two ways we can do it. Decrease the mass of the objects or increase the distance. The second one, we want to increase the gravitational force. Well, you're going to increase the mass or decrease the distance. And so those are the two things that we talked about in class also. All right, we want to know the asteroid's belt period, so we know this is really Kepler's third law of planetary motion, p squared equals a cubed. We know the distance from the sun is 3, so 3 cubed is 27. So we know p squared equals 27. Take the square root of both sides, and it's approximately 5.1 years. And you did a few of those in class also. Here we want the most circular orbit. Well, this goes right on back to Kepler's laws of motion, where you guys actually calculated eccentricities. And one thing that you notice as the eccentricity got close to 0, it becomes more circular. I mean, if you look at a circle, the distance between the foci does not exist because both foci really are on top of one another. So we want the one that's the closest to 0. And if we look on here, it looks like 0.007 is the closest to 0. So we would expect that to be excuse me, the most circular. Elliptical is the value that's the closest to 1. And if we look on here, Mercury's 0.206, and by far that is the closest to 1, so that Mercury is the most elliptical. This goes right back to Kepler's laws of motion and also the eccentricity activity you did. Here we asked, where's it the fastest? Well, as you decrease the distance between the planet and the sun, the planet's going to speed up. And as you get farther and farther away, the force of gravity becomes less and less, so it becomes very slow until it makes that turn and starts to go back towards the sun. So the fastest part is closest to the sun, and the slowest part is the farthest. And this is really what you looked at when you did Kepler's second law of motion. The last question here was the eccentricity lab. You actually did 6 of these. And my little rough graph here. The distance between foci. So the distance between foci is 1.5 to -1.5, which is an absolute value of 3. We need the length of the major axis. So that's from 2.5 to -2.5, so that absolute value is going to be 5. And we know the eccentricity is the foci distance divided by the major axis distance. So 3 divided by 5 is 0.6. And again, that gets into Kepler's first and second laws of planetary motion and also the eccentricity activity you did. So there's my little review of the first assessment there. Many of you did very well on this, and if you're going to retake the test, it'll be similar, but not quite. It won't have the same questions. So with that, I think we will be done.